Aloha. As most of you know, I'm Dr. J.D. Armstrong. I'm the Maui Technology Education and Outreach Specialist, and one of the things that I get to do is put together these public talks for the community, both the local community and our web community now, thanks to Stephen Moore. This week's speaker is Dr. David Dearborn from Lawrence, Livermore. And we have to give a nod of appreciation to Steve McGee for getting us in contact with him. So this is why you don't do, if you're a scientist, you don't go on tourist attractions around Maui, because I have my people out looking for you. So I think the best introduction I can give for Dr. Dearborn is the one that he suggested as I was driving him up here from the airport. Lots of school, lots more school, and then Lawrence Livermore Labs. But he's also doing, in addition to this research on thermonuclear deflection of asteroids, or as I'm calling it, the Nuka Rock Talk. He's also doing interesting work on binary novas and quite a few other things that I'll let him talk to you about, because I'm sure I've made my minimum of one mess up on this already. So, all right. So aloha and thank you.
Thank you. Well, it's a pleasure to be here, and let's see, I'd like the microphone to stay near me. It's a pleasure to be here and share with you this bit of work that I do. And I hope that by the end of the evening you'll understand why I put forward nuclear deflection as one of the candidates. And in fact, the National Academy study that reported to Congress in 2010 basically concluded that if a large asteroid were seen coming our way, you know, not one of the weeny little things, a Tunguska-like thing, but if a real manly asteroid that was going to eat a continent were coming our way, the only thing that we have that can deflect them are nukes, used correctly. And if you watch the movies, you can see all the ways to use them incorrectly. But there are ways, I hope you'll feel when I finish, to use them correctly in this. Okay, who is Dearborn and what does he bring to the study of NEOs? Well, I was trained in theoretical astrophysics, and while I do indeed enjoy getting out my 10-inch telescope in the backyard and taking pictures of things that everyone else has taken pictures of, I spend the greatest amount of my time sitting on a supercomputer trying to model things in 3D these days. And so I'm working with students at UT to study pair instability supernovae, with students at Monash University studying proton ingestion in advanced red giant burning stages, and, you know, things of that sort. I love theoretical astrophysics. But as I said, that's what I was trained in. However, when I went to Livermore, I also became a nuclear designer. And I have designed nuclear explosives and tested them. I've also designed conventional explosives and tested them. I also am here because the lab's sending me out for missile tests, which they do. I have gone out to the Marshall Islands 2 to 4 times a year for the last 17 years associated with missile tests. And so I know something about nuclear, and I know something about missiles, as well as astrophysics. Not that it matters here. I've also done a great deal of work in archaeoastronomy, so you can buy my book on the Inca, although it is out of print and it is pretty expensive, so probably you don't want to buy it. Okay, what's the talk about? Well, I want you to know what asteroids are, how are asteroids found, and why are they a concern? Once you found one, and if you feel like doing it, how do you move it? And then finally, why consider nuclear explosives? So those are the things that I hope you'll have as takeaways from the talk. Now, in terms of it being more than academic concern, we know of something like 150 craters on the Earth today. And when we look at the moon, we can see lots more craters, including some that are 1,000 kilometers across. we have to figure the Earth is a bigger target than the Moon. And so the Earth probably has been hit by all of those and a whole lot more. And we don't see the craters because they erode. So things like, the Atlantic Ocean, it's young. There used to be one continent back when dinosaurs were running around. And so that whole Atlantic Ocean is not much more than 100 million years old. And so a lot of places where craters have impacted, they don't exist anymore. They were hitting at high rates. They continue to hit at a low rate. But, there are some that we should worry about. Back when I was a student at UT and would drive out to McDonald Observatory, I'd drive basically through this crater on the way. At the time, they didn't know it was a crater. This is Sierra Madre crater in West Texas. It's 13 kilometers across. And when you drive into it, that's the central uplift in it. At the time I was a student, they thought that was a volcanic uplift. But you know how they are in Texas. They go drilling everywhere. And they drilled down, and they didn't find oil. They found shock breccia. And said, oh, shit, just an impact crater. This is a weeny small one. I mean, if this thing happened today, no one in Texas would enjoy it. This one, when it first formed, the one in Sudbury, was about 250 kilometers across, still smaller than those ones that we saw evidence of on the Moon and that no doubt existed once upon a time on the Earth. That type of crater is right up there with dinosaur eaters and eliminate large sections of mankind. Okay, so we want to know, these things have happened in the past. What's the chance of one happening in the future? How can we know about it? And is there anything we could do about it if we saw it? Well, the first thing is to find them. And in 1998, NASA began funding an effort with the goal of trying to discover 90% of the near-Earth objects that had diameters greater than a kilometer. And they wanted to do it by 2008. They didn't actually quite finish by 2008. They think they've finished now. And it was done mostly with 1-meter class telescopes that were diverted to doing a robotic job of searching the sky each night and reporting whenever they found something that didn't stay steady, and sending it to the Minor Planet Center. The Minor Planet Center chewed on it overnight and handed it off to JPL if it was coming too close to the Earth. Okay, and that effort started in about 1998. In 2005, Congress went further. That is to say, they asked for something without providing money. And in this case, they said, well, 1-kilometer asteroids are going to be a bad day for everyone on Earth if they strike. So what about something that's merely 140 meters across? Now, there are some people who've tried to figure out why they said 140 meters. The best answer I've come up with, or I've heard someone come up with, was that 140 meters destroys the average size congressional district. And, no one wants that. And that is by telescopes yet to be named. Although pan-stars, the growing form of pan-stars would be one. I have a picture of the hallucinated LSST, because my lab's involved in designing the optics for the LSST, which would be another candidate for contributing to the survey that the Congress ultimately wanted. So once you start looking, what do you find? And about 1800, if you'd looked at the solar system, the inner solar system, this is what you'd have seen. The sun in the middle, Mercury, Venus, Earth, Mars, and off the screen here would have been Jupiter, down here somewhere. Okay? Well, beginning about 1803, they started finding things out there beyond Mars and inside of the orbit of Jupiter. And at first they said, aha, the new planet! And then they sort of looked and said, well, it's kind of small for a planet. And they started discovering other ones that were also kind of small for a planet. And by 1900, you had this area out between Mars and Jupiter becoming populated with what's called the asteroid belt. Well, old guys keep looking. And by 1950, that's what the inner solar system looked like. And you're beginning to see some red dots in here. Now, the red dots are distinguished from the green dots. The green dots are asteroid belt objects. The red dots are things that are called near-Earth objects. Now, that doesn't mean that they cross the Earth's orbit. What it means is they come in, and at their closest to the sun, they at least reach partway between Mars and Earth. Okay, 1.3 astronomical units is the definition. And some of them come in way into the inner solar system. But those are the near-Earth objects that people were interested in. By about 1990, that's what the solar system looked like. 1999, 1 year after they started the survey, that's the inner solar system. And the numbers here are old. That's 2010. Today, this number is about 570,000 objects known, most of them out in the asteroid belt. Of the things that come into the inner solar system and are near-Earth objects, the number is something over, it's near 7,200 objects now, of which about 914 of those near-Earth objects are larger than a kilometer. Worse yet, there's a subclass of the near-Earth object called potentially hazardous objects. And people just love initials. Potentially hazardous objects, and the number there is up to 1,244. And these are objects that pass within a 20th of an astronomical unit of the Earth. And so their orbits not only cross the Earth's orbit, but they do so close enough that there is concern that they can become intersecting orbits. And intersecting orbits are bad. So what are asteroids? Well, there's a picture of Ida. Lots of asteroids are these, the very big ones are spherical. They have enough gravity to make them spherical. But when you start getting smaller to things, and this one's merely 58 kilometers long, again, that one comes at the Earth. That's an extinction of life type event. Fortunately, it's out in the asteroid belt. When you have something that's long like that, it's kind of difficult to work around because if it's spinning, and you know, there's only one way you can not spin, and an infinite number of ways you can spin. And so you might guess most things spin. And you know, and now we're going to talk. This is the part of physics courses where you see kids in classes and they're doing things like that, and thinking about cross products. And if you look at the moments of inertia of that body, if the spin is not well aligned with it, it does what this guy was doing, which is both spinning and precessing. I remember one astronaut when he wanted to put a rocket engine on it and push, and said, well, where would you do it? And he said, well, I go right to the pole, push along the pole. Well, pole may not be pointed in the direction you wanted to push, and the pole isn't always pointed in the same direction anyway. So not a good idea. Okay, so you got to deal with that. The gravity is not very high on the body. As I say, you know, we're not typically looking to move 50-kilometer bodies. It's that 900 or so that are more than a kilometer in size. And you ask, well, okay, how much does a fat boy like me weigh walking around on the asteroid? And the answer is a little over 1/10 of an ounce. Okay? Now, 1/10 of an ounce I lift real easy. And you say, what's escape velocity? That. Okay? So you can actually jump off of the asteroid real well. You ask about, well, what about going into orbit around it? Well, if you go out far enough, not a problem. But in close, something that's that shape and tumbling, there's no stable orbits near it. So you have to be actively controlled the entire time that you're trying to stay near it. And so those are some of the challenges of working near an asteroid. Are they rocks or rubble? The answer is probably most of them. Most of them are thought to be rubble. Okay? But, and you look at something like Itakawa, and you look at that and say, well, if a dump truck didn't lay that one down, I don't know what did. But if you start looking at the densities of the ones where we have a size and we have a mass one way or another, some of them are up over 3 grams per cubic centimeter. And that's basalt, solid basalt. Now, it doesn't mean it doesn't have cracks in it. Doesn't mean it's one big monolith, you know, but because big rocks tend to be fractured. But that's not a pile of gravel at 3 grams per cubic centimeter. Granite, you all heard of granite. That's 2.6 grams per cubic centimeter. And there's guys down in that neighborhood. And that, again, isn't what you have for gravel. Now, when I ordered a bunch of gravel brought up to my place and put on so I could put it on my drive, that comes in between 1.5 and 1.9 grams per cubic centimeter, depending on the grade and whether I've got a bunch of sand in it or not. And there's a lot of guys that have densities that fit with being gravel. There is also an piece of evidence that people have used for years and said, I don't think there's a lot of tension that hold these things together. It's mostly gravity, and that's looking at the rotation. And so if you've got a guy that's rotating, and you say, fine, for density 2-ish material, when does the centrifugal force equal the gravitational force? So if you spin it faster than that, it'll fly apart. Okay? What period is that? And it's about 2 hours. And it's actually fairly insensitive to the density. And so as you look at asteroids and you see the number at 4 hours, and you see the number at 3 hours, and you see the number at 2 hours, they're going up. But you get below 2 hours and the number drops way down. As if anything that spins faster than 2 hours, in fact, once upon a time they'd have said anything that spins faster than 2 hours falls apart, i.e. they're rubble, they will fall apart. Well, naturally, when people started looking, and this is an old list, I started looking again, and there's a bunch of new ones. There are things that, 1/10 of an hour, 3/10 of an hour, 1.6 hours. Here's a 900-meter one spinning at half an hour. Those things need tension to hold them together. They are not rubble. Okay, it don't need a lot of tension. I mean, enough rubber bands could do it. But they are not solid rock, or they're not gravel. They have some tension to hold them together. So at this point, what you say is, yeah, I've got to be prepared that if I want to push one of these things, that the only thing holding it together is gravity. But I don't know that that's always the case. So I want to look at both cases. Okay, when you have a thing that's orbit seems to cross the Earth, it's actually a three-dimensional problem, and it may go in under and come out over the top of the Earth. Okay, but those orbits precess, and it maybe thousands of years precession time, but they precess, and when they precess, they go through intersections with the Earth's orbit, and during that intersection period, if the phase of the asteroid and the phase of the Earth are just right or just wrong, you will have spectacular events, okay? And so when they defined PHOs, they're looking at things that when they pass the Earth's orbit, they're close enough that they could precess, and you say, well, you really should keep an eye on this guy, maybe more than, looking once or twice and then forgetting about it. So how do you know what an asteroid's orbit is? Most asteroids, especially when you're dealing with 1-meter telescopes, you only see some distance out. And if they're a small asteroid, that's a small distance. If it's a larger asteroid, it's a somewhat larger distance. And so there's some distance out to which you can see it. And so if you've got the Earth's orbit and the asteroid's orbit, and they're coming along, and these fellows that are scanning the skies look out, and they catch it, and they say, there he is, let's track him, let's get him tomorrow night, the next night, and they track him generally as long as they can. In some small cases, small bodies, that may be a week. In larger bodies, that may be a couple months that they track them. And so they have an arc, a little piece of the orbit. And with that little piece of the orbit, they can project the orbit around. But there's always uncertainty in measurements. Whatever you measure, you may say, yes, this cabinet is 36 inches. But is it 36 inches or 36 inches and a 25th? Mostly it's not 36 inches. And so when you're making the same measurements over here of where that thing is in the sky, there's always an error. Those errors, they try to keep in and propagate out. And so they've got a range of orbits that it might be from that small arc. And so what they do is they then predict and say, okay, it's going to come back, and this one that's got a slightly larger semi-major axis is going to take a little longer to get back. And so we'll wait until we see it again. And when we see it again, we'll be able to know which of these guys it is. And so you have to see them, and your first orbits are poor. And in fact, those first orbits, as they then project them forward and say, well, where's that thing going to be in the next 100 years? If it's got a big uncertainty, You know, if you've really observed it well and it's got a small uncertainty, and you say, fine, where's the path going to be in the next 100 years? And it grows slightly and grows slightly. But if you've got only a really short bit of track, it grows rapidly and grows rapidly, and suddenly the Earth is in it. And so you say, there's a probability of hit. So if you look at the Sentinel system, which I'll mention a little bit later, and look down there, quite a number of the bodies that have some finite probability of hitting the Earth are these type of fellows. They've only had a brief encounter. They project them out, and they say, well, formally, we can't say it's going to hit the Earth. We can't say it's not. But you know, we are saying we should get another look at it sometime. And so these guys are often uncertain. If you look at orbits and say, well, how big is the error? And there's a nice logarithmic chart, so you can force lots of orders of magnitude into a single graph. And basically, as you get out to about 10 orbits, the uncertainty in where that body will be next year gets smaller and smaller and smaller, and by 10 orbits it gets down to about 1,000th of an Earth radius per year, which suggests that you could predict it was going to hit the Earth or not 1,000 years out. And that would be the case if you knew all of the things in the solar system and it was only gravity. There is a more interesting universe than one that has only gravity, though. Among the things that there are in the universe is light. Sun puts out some of it. That light hits the asteroid, pushes on it. That changes its orbit. And if the asteroid were painted white and it reflected the light, there would be even more momentum transfer to the asteroid, and so it would push it more. In fact, most asteroids are very dark, and so the light gets absorbed, and then you ask another question. What's the surface like? And that's awfully hard to tell from a telescope. So if the surface is sandy, surely some of you have played in sand here. And if the surface is sandy and you see what it's like when you're playing volleyball on the beach on a hot day, and that surface heats up, the very top quarter-inch of sand is really hot. Get your feet under it and it's okay. That's because there's poor conductivity. If it were a solid rock, the energy would absorb in deeply and it wouldn't heat up nearly so much. So if it were sand, it's first of all re-radiating out this side, and when you get to the sunset side of the asteroid, where the asteroid's rotating around and the sun sets, that side is hot and is radiating, and it's like a rocket pushing it that way. And the sunrise side is cooler, and so it's pushing less. And so this is an unknown thrust mechanism, and on 100-year timescales, this is significant. And so it makes it impossible to predict exactly where a thing's going to be far enough in the future. And as an example of that, there's an asteroid, 1950 DA, that got 50 years of data on it. And with the standard calculation that JPL puts out, it has a probability of 1 in 300 of hitting on Saturday, the 16th of March, 2880. That's what, basketball season? Could ruin it. Then they said, well, but, let's be serious. What happens if we start adding things like the center of the sun is rotating fast and is a little oblate, and that changes the gravity just a little bit. I mean, it causes a general relativistic term that causes Mercury's orbit to precess. But if we add that, well, it changes it by enough to miss. What about adding 61 asteroids to the calculation? The largest asteroids. That changes it way more than enough to miss. What if we include the uncertainty in the mass of the planets that it passes by? We come down to the Akatsuki Effect, which is that re-radiation of light that I was talking about, and we don't really know which way it's rotating, which way it's thrusting, and how much. And well, it could miss anywhere from 9 days one side of the Earth to 57 days the other side. So, it's not a serious prediction that it's a threat even 800 years out. So, JPL's response is to only worry about it up to 100 years out, and they've produced this Sentinel system, and it has a list of a fair number of asteroids that have some finite probability of hitting. Some of them parts in 4 parts in 10,000 that they will hit in the next 100 years. And, well, that's better than winning the lottery. But again, it's not enough to say, maybe we need a space mission to that guy to find out for sure. Maybe we need to observe it a few more times to find out for sure, between now and when they project the hit, possibly. Okay, so when we observe the asteroids, most of them we can look at and say, hey, that body ain't going to come near us, not in the next 1,000 years, write it off. But there are some out there, a small percentage of the total, that we can't say that. And so they're keeping a list and they're watching it, and if someday the probability reaches a certain threshold, people are going to argue maybe there should be a mission to resolve this. So, but that hasn't happened yet. Impact rates, well, as you might guess, small ones are a lot more common than large ones hitting. There's a lot more small bodies than large bodies. Small bodies that deposit kilotons happen every year, and 10 kilotons every few years. And the reason that we don't hear more about that is when a body that comes in and deposits a kiloton, it's only 4 or 5 meters across, and it's breaking up 30 kilometers up, and it's depositing that energy 30 kilometers up, and 30 kilometers is a lot of weight, a long ways away for a kiloton. I mean, I know most people in San Francisco wouldn't believe me, but if I set off 10 kilotons 30 kilometers above San Francisco, there'd be a big bright flash, but no windows would break. So, it's not a threat. This thing, there was, in 2008, a body that was seen coming in. It was discovered about 20 hours before impact and observed. And, in fact, amateurs were important in picking up some of the observations for that body. And it was predicted it would break up over the Sudan. It did so. There's pictures with a cell phone of the trail that was left in the sky. People went out and collected up little bits of debris that landed, about 10 kilograms of it, and it was about a kiloton worth of flash up high. So those things happen every few years. If we come up to the 3 to 10 megaton range, those things actually touch the ground. Tunguska happened in 1908, flattened about 2,000 square kilometers of forest. If it had happened over New York, it could have flattened 2,000 square kilometers of city just as happily. The difference between the Barringer crater and Tunguska is Tunguska was clearly a very friable bit of stone, broke up on the way down. It probably deposited most of the energy at about 6-7 kilometers and sent a shock wave down. The fireball part didn't touch the ground, and the fireball went up. Barringer crater was an iron nickel. It just came all the way down. And by the way, the 10 megatons comes from a estimate of a fellow who was at LBL and is now at Purdue, Jay Melash. And most of the bombers I know say, I'd like to be able to make a hole that big for 10 megatons. Most of them believe it was somewhat higher than that. But in any case, those type of things happen every few hundred years to 1,000 years. Okay? And again, most of them, when they happen, are going to be over the ocean. So, that type of thing happening over the ocean is not a global issue. When you get up to 1,000 megatons, you're now talking tens of thousands of years. The circle on there that includes L.A., Carson City, Sacramento, San Francisco, that's the circle of 10 psi and 40 calories per square centimeter, just using the standard bomb book, the circular slide rule that Dr. Strangelove had. I got one. That's what it says. Everything in that circle, all the houses would fall down and burn up. Okay? So that would be regionally poor. Still not a global consequence. by the time you get up to 1 million years, you're now starting to talk about things that exceed a kilometer in size hitting. And there, people actually don't know the extent of what will happen. They believe it will be global. They know if it hits in the ocean, there will be something that is technically not a tidal wave, but if you're at the coast and a 40-meter wave comes over you, you probably don't care that the wavelength isn't long enough to be a proper tidal wave. It's the type of thing that hits. It will throw up lots of stuff. It will come down hot, and it will burn things a long ways away. It will leave lots of dirt in the atmosphere. You will have weirder weather. And so, by the time you're getting the million year, you're now talking about things where in a world that's choked with 7 billion people, you're going to start talking about losing billions of them with the consequences of that. And you get out to tens of millions of years, and that's where you get the much bigger things, these several kilometers to 10-kilometer range. And the Chicxulub Crater was thought to be about a 10-kilometer object. And that, again, they see 20 foot of sediment washed up on Cuba, and, it was a big wave. And it was probably bad on the other side of the Earth. But those are rare.
That was the one in Yucatan?
That's the one in the Yucatan.
The dinosaur one.
The one associated with the dinosaurs. Okay, risk factors. I once spent a whole day trying to convince a general energy is equal to 1/2 mv squared. V important. So the bigger the mass, 1 kilometer, has 1,000 times the mass of a 100-meter object. So 1,000 times more mass, more energy. Velocity. The velocity ranges that things can hit with ranges anywhere from 10 kilometers a second to 72 kilometers a second. Now 72, the Leonids, that's a shower that's just about now. The Leonids impact the Earth at about 70 kilometers a second. And that's about as fast as anything can impact the Earth and still be part of the solar system. And so you say, fine, that's quite a range. Let's take 20 as a standard number, okay? At 20 kilometers a second, 1 kilogram rock carries as much energy as about 50 kilograms of TNT. So a 1 kilogram rock that somehow comes and hits the surface of the Earth creates an explosion that's equivalent to 50 kilograms of TNT. Now, when we're talking a 1 kilometer object, you're talking about not a kilogram object, you're talking about a billion-ton object. And so when it hits the Earth, it is sort of 50 billion tons of TNT equivalent, which, we take everything Russia ever made and everything we ever made and put them in a pile, and it's still small. Okay, so that's why they're big. This, by the way, is a crater. That's a road. That's a big stand that lots of people can get on, and that was made with 104 kilotons. So kilotons of energy can create big holes. So how do you change an asteroid's orbit? And here's where we're stuck with that slime Newton. He causes problems. He requires us to conserve momentum. So if I had a kilometer scale thing, and I took a Saturn V rocket and I crammed it in, and I said, okay, burn, and I wanted it to miss in 35 days, and I took out an extra 2.5 million tons of fuel for it, I could cause that asteroid to miss us with only 35 days of blasting, of pushing, assuming it wasn't rotating. Okay, another way to look at this is that's about 5 supertankers delivered to deep space. If you can get out there earlier, it's better. The amount of speed that you have to give it is much smaller. And so 7,000 days, about 20 years out. And there I only need about 10,000 tons of fuel. Okay, that sounds a little better, But remember that the things that we send out to deep space, the missions with fuel, tend to run about 5 tons. So 10,000 tons is a lot of effort. There's going to be a lot of launches to get that out into space. So, we have to think about how we push this thing, but we do have to conserve momentum. There are ablative proposals, and the ablative proposals say, well, what if I heat one side of the asteroid and vaporize it and it blows off? There I'm not carrying the mass out with a rocket. I'm carrying the mass of rocket fuel out, and, it's $1,000 a pound or more to lift rocket fuel into low Earth orbit. Getting it into deep space is expensive, not cheap like low Earth orbit. And what if I can put a lot of energy onto one side of the asteroid and heat it up? And people have looked at that. They've proposed lasers. And again, for the kilometer class object, you need to vaporize about 5,000 tons or 10,000, between 5 and 10,000 tons of rock. And as it turns out, that requires 5 to 10 kilotons of energy. And with the National Ignition Facility, the largest laser in the world at my lab, the way it's currently designed, they can indeed put that much energy through that laser in about 6,000 years. So we need to work on that. A cuter idea was to fly 50-meter mirrors out to the thing. Now, I know 50-meter mirrors weigh a little bit. And when you get them out there, you have to steer them actively because the asteroids are rotating and you need to have the spot in one place. But, and then let's assume all that works. The place where Jay Milosh got stuck with that was, he said, well, what if it works? What it does is it heats that spot and outgasses, and lots of gas and vaporized rock comes off, and it's coming off on the same side as the mirror is. So you need a whole bunch of mirrors once you've coated them with rock, or you got to have some people out there to refinish it. In any case, there are challenges there. Why consider nuclear explosives? They're a mature technology. Nuclear binding energy in physics is the strongest binding energy known. It's millions of times more stronger than chemical binding energy. So pound for pound, if you had fusion, it's about 3 million times. So if I could take somehow my gas tank and switch it for an equivalent mass of fusion energy and drive the car equally well, on one tank I could drive to Jupiter and back if there were a road. So it's a very efficient way of transporting energy, and as long as payload is an issue, this has to be thought about as a way to transport energy. And then the question is not what nuclear explosives do. We know what they do. That's not a problem. We don't need to test them, at least right now. We pretty well know. If you send this type of nuclear explosive out, it'll make this big a bang, this many X-rays will come out of it, this many neutrons, that many gamma rays. And funny thing, in outer space, you pretty well know how those things travel, in a straight line. And so they absorb on the surface of the asteroid, and you can vaporize a thin layer on one surface of the asteroid. In fact, because it thickens the layer, I actually prefer the type of nuclear explosives that put out lots of neutrons. They go in deeper, and they kick off a little more mass at a lower temperature, and it gives a better impulse. So nuclear explosives have been tested in space. One of the first times I gave the talk, I said, yeah, but no one's ever tested nuclear explosives in space. How do you know they'll work? There's 4 megatons. Yep. I got a picture of Johnson Island, the incinerator on here too. And the effects are known from experiments, so that's not the question. The question is the asteroids. When you push an asteroid, how does the asteroid respond? And it's the same question that people who want to use impactors have. The Deep Impact mission went out sort of sent a big hunk of copper into a small comet. The comet was small, but not that small. And so it kind of went along and he said, yeah. And there's no measurable change in its orbit, but there wasn't any expected. Nevertheless, large impactors on small asteroids could be used. The question is, when you impact the asteroid, how does it respond? So the question here is, how does the asteroid respond? Not what the nuclear explosive does. We know what the nuclear explosive does. Puts out lots of energy. Lots of energy hits surface. You know, R squared goes out straight. And heat surface turns into gas. Gas expands. Momentum. Some momentum go that way, some go that way. The total amount of momentum that you get out, though, depends on a lot of things like porosity, and I'll come to that in a minute. So the questions really are on the asteroid. So I'd say Livermore has interest and experience in nuclear effects. We've made craters. There's a crater we made. There's a crater we made. That one's with an impactor. And so if we need to change the orbit of the asteroid, we hope to discover it coming decades out. If you discover it's coming decades out, the speed change that you need to make it miss the Earth is a centimeter a second or less. So it depends on the orbit, and there are some orbits that are pathological and take more. But, 3 decades out, maybe 3-5 millimeters a second, typically, speed change, will cause it to just miss. So maybe you'd like a centimeter a second even there. Okay? And so decades out, you do a standoff nuclear burst. That's where you don't go down to the surface. You pick a distance where you say the fluence, I picked a nuclear explosive, it has this yield. I want so many calories per square centimeter on the surface. I will pick the distance. I will tell it, watch as you're approaching, and when you get to this distance, go off, heat that surface, cause a gas, have it blow off, and give it a nudge. And the idea is to give it a nudge that it changes its speed by that centimeter or so a second. Okay? If, on the other hand, for some reason you don't see it coming till it's less than a decade, now the speed change that you need gets very high. And it becomes very difficult, especially if it's not a very large asteroid, it becomes difficult to push it several centimeters a second, maybe 10 centimeters a second, and have it stay together. And if you're going to break it into pieces, you want to break it into pieces robustly. Because if you break it into just barely into pieces, all the pieces are coming at just about the same speed, and so they may all still hit the Earth. No win. I mean, there were people where I worked that studied something called MIRVing, and they knew that was a real good way to increase damage. So we don't want to MIRV the asteroid. We understand that. You don't need to tell us. We don't want to MIRV the asteroid. What you want to do, if you are in a position that you say, I have no choice, it's either take the hit or break it up. If I break it up, I want to break it up robustly so that it, first of all, is made into smaller pieces, lots smaller pieces, so that hopefully they won't get through the atmosphere. And secondly, I want 99.9% of it to miss me. And I figure that's an improvement over the whole thing hitting me. There are some people who've argued that with me. Okay, so how do you nudge them? Again, you heat lots of mass. More mass ejected, the greater velocity change. The heating for the 1 kilometer sized body is 5 to 10 kilotons. Guess what? That's no problem for me. I can produce 5 to 10 kilotons on the surface, standing well back. That's just not a problem. There is an optimal height. If I back off too far, the flux that hits the asteroid is too small. That doesn't heat it much. If I come too close, I put a real sharp impulse in a spot. That sharp impulse runs through and probably breaks it apart, but it's actually not as good a push. Okay, in doing this, I have to deal with simulations, and this is actually I'm happy with this from a 3D modeling of a burning shell in a giant star showing mixing that wasn't supposed to be there. And so it finally solved my thesis 35 years after they gave me my PhD. I went back and told them I was happy they gave it to me on spec, but I finally solved the problem. So we know how to do 3D. We know how to do 3D calculations, but 2D is faster. And most of what I've done in the past has been looking at the systematics, the material science. So I've looked at things that are a kilometer in size. I've looked at smaller things, 270 meters in size, that just meets the Apophis size things. I've typically looked at densities with a high density core and a lower density, sort of a sandy gravel type of surrounding. The bulk density of this object is about 1.99 grams per cubic centimeter. The bulk density of Itokawa, that 500-meter object that the Japanese visited, was 1.95 grams per cubic centimeter. So it's actually fairly close to that. The calculation was done standing off and pushing at it over a large area, or in placing it right in the surface. That is to say, I did not envision bringing Bruce Willis along and drilling. Because as I said earlier about fat boys and tenth of an ounce, if we got Bruce and his boys there and they put their drill rig on the surface and they said, okay, run her in, and the thing would go down and it would launch the whole drill rig. So I figured I'd just bring a bigger bomb than Bruce. So we're going to look at both the breaking it apart and the standing off and pushing. And we do that in the context of no-strength models. An example of no strength is walking on water, something very few people can do because it doesn't have strength. And so when you walk on water, you just sink right in. It provides no real strength. Gravel acts like a fluid too, but it has a strength in the sense that when you step on it, rocks begin to slide as you put your weight on it, but then the pressure of your weight causes friction between the different pieces of gravel, and you get a pseudo-strength just associated with the friction from the pressure. And so you get strength in compression and no strength in tension. And so we have a linear strength model that mimics gravel and sand fairly well. And then we can go ahead and model full strength things as well. The biggest question on full strength things is, when you have stressed them to points where the elastic limit is reached. You just, where the cracks start, you don't really know. So with the standoff, you start the thing going, and you heat a thin layer on the surface, and shocks go in. And in depositing 11 kilotons into this thin wedge on the surface, about 41 degrees out, so it would be equivalent to the explosive going off about here.
About 2 radii?
Not even 2 radii. About half a radius. Oh, pardon me, about a radius. I was thinking diameter. Yeah, about a radius. The general, without strength didn't matter for the nudge case, and 11 kilotons was too much. I typically got 2 centimeter a second speeds. I lost 2% of the mass. That is, 2% of the mass came off. All the brown stuff there stayed. All the white stuff came off. And I tracked that around, and of the stuff that came off, about 100,000th of it still threatened the Earth. So 1/100,000th of the 2%. Okay, so we'd have had a good meteor shower. I actually have had people from NSA saying they'd rather it hit than threaten their satellites.
I see. But in terms of that material, do you have a projection as to what the particle size is, typical particle?
No, I mean, the best I do is I say, look, when you look in space, there's, most systems you look at have a size spectrum that's about -2. And you divide it up that way, and you fly it around and you see what hits. And so that was a little too hard. This was with no porosity, though. When I put porosity in, porosity is a property where I was actually demonstrating it for some people from National Geographic once, and I was in my backyard shooting a pillow, and showing there's no coupling. The thing goes right on through, and you don't get much push. And things that are porous, when you press on them over a wide area, you lose a lot of energy by crushing up, but you don't get a lot of rebound, so you get less momentum out. And so in the case when I put porosity in, these numbers drop from 2 centimeters a second down to about 8 millimeters a second. And that is an uncertainty that you're going to have if you don't have a mission. If you have an asteroid that's threatening, having a mission there that goes and characterizes it would be a really good idea if you've got 20 or 30 years and 3 or 4 launch windows. The first launch window, get something out there that can study that asteroid, tell you its mass if nothing else, maybe a little bit about its internal constituent, how fluffy it is, how porous it is. So, but if it's porous, it's not a problem to get a centimeter a second. I just push harder.
Yeah. Bigger yield.
Yeah, I come in a little closer. Same yield, come in a little closer. Bigger yield, same distance. Either way. So a nuclear standoff, or nudging it, is the preferred approach. It eliminates essentially all the impact. You would want to detonate it at an optimal height, and that's basically set by how much flux do you want on the surface, how much gas do you want to heat up, how hard do you want to push it. And you could do repeated nudges. Dealing with the military, they often want to make sure of something, and so they say, well, let's send 2. If the first one does it, let the second one go.
Well, perhaps 2 in a given mission, one to give the characteristics of the body, and then the second one dial a yield.
You would probably send something ahead that characterized if you had time, and then more than one, and if you were dealing with impactors, again, for smaller bodies, 100-meter bodies, it is plausible that we could send enough impactors to modify the orbit 20 years out. The nuclear could do it also for the large ones, but or for even for small ones. But I have been perfectly candid, and I still believe if they want to try impactors, go ahead and try impactors. If it's it's less politically sensitive, not a problem. If they have problems with the impactors, just give me a call. We'll deal with it. Okay, what if there's less than a decade? And a case where you might think of there is the Apophis, wherein this is an old number. They've actually reduced it now, so it's even less likely that it's an issue of any form. But it's a 270-meter object. In 2029, it passes between us and the geosynchronous satellite distance, which led some kids, a talk I gave, to ask if it was going to disrupt television that night. There is a 650-meter spot off of the Earth somewhere that if it passes that, its orbit will be bent in a way that it comes around 7 years later and hits the Earth. Okay, it's called a keyhole. And it's fortunately an uncommon size keyhole, or an uncommon keyhole. But that's an example of a case where you just wouldn't know. 7 years, and we're going to have possibly a new sea level canal in Costa Rica. So don't wait too long to deal with it. Low Earth orbit is too late. So, again, if you wait till you're in low Earth orbit with the shuttle, as in most of the movies, and you break it up, all the pieces still hit. And if you break up a 1-kilometer asteroid and smear it out over one whole side of the Earth, and let's assume I break it up into pieces small enough that none of them get through the atmosphere, the energy is still enough to burn down everything on that side of the Earth. So it's probably not a good idea. So go out a ways. And this is an example of taking an Apophis-size object and putting 300 kilotons in the surface, and put it into a region 1 meter in diameter and 3 meters deep. and said, go put 300 kilotons in there. And most of it turns into a plasma quickly and vents out. But that venting out creates a very sharp impulse that goes through, and it's pretty tough on the rest of the body. And pretty soon it will get out. I'm changing time scales every now and again. Okay, faster, faster, faster. At this point, we turn it into a 3D debris field, and we put it on an orbit, and we sail it in from 10 days out, 15 days out, 20 days out, 30 days out, 40 days out, and say, how much hits on each of those things? And here it comes in, and I'm going to change scales again, and there it goes on by the Earth, and that's mostly gravitational scattering, but when you break a thing up, the debris field is such that the Earth goes through the debris field, and that's worrisome. But if you make the debris field large enough, which means 15 days out was really too short, that's the material from the body that actually hit. And 15 days out, 3% of the body hit. If I had gone to about 30 days out, the total energy hitting the Earth over a several-hour period, the total mass was less than the Tunguska mass. So nothing would probably penetrate the atmosphere, at least statistically, on that. So those are the distances you want to get out. Getting out 15 days is not a short distance. 15 days in travel is like 15 times or more the distance to the moon. And, the moon's a long ways away, as things are. So if you're trying to go out 15 or 30 times the distance of the moon, you're talking about a lot of extra fuel. And if you have a 1 kilometer object, I don't want it to get, I want to be able to deal with it at least a year before impact in order to make sure that the amount of material that's hitting is negligible. And so we have done models of surface bursts on 1 kilometer objects. There, you don't want to mess around with 300 kilotons. Go for the megaton. In this over here, it was red and yellow, kill a fellow, blue and green, miss you clean. This one had a solid core, which would be an unpleasant surprise if it were right at the center, because the shock goes through the core, it breaks it into fragments, it spalls things off. You all watch Newton cradles? Yeah. These things where you set the balls going? And I did a Newton's cradle there, and the center was broken, but it wasn't dispersing. It was actually still bound, so it came in. And it was actually moving backwards from the original speed by about 8 millimeters a second, which on some orbits it would miss and some orbits it wouldn't, depending on how far out. So it would be nice, the fracturing should only be done if it's late and you just say, I really don't have any other choice and I want to, but you don't do it still too close. You've got to get farther out. And that would be a case of wanting to send 2. With less time, fragmentation can reduce catastrophe to inconvenience, I'd say. 1 megaton reduces impact for a kilometer object to between 1 in 10 to the 4 and 1 in 10 to the 5. Higher yields reduce the threat more. When breaking it apart, it's important to know the structure. Are there big lumpy bits inside? That would be really desirable to know. Don't send just 1. With less time, you can repeat. So anyway, it's only natural. There'll be another large impact resulting in global catastrophe any million years now. But don't panic. Coming from Livermore, I would say Los Alamos man here will develop a forebrain in that amount of time. Nuclear technology provides an ability to deflect most NEOs. They're well tested and characterized. We don't need nuclear tests. We know what they put out. We know their output. More precise information on the asteroids is what would be desirable. So with current technology, we can handle most possible threats. But even with the nuclear option, it requires some time to get it ready. So it is not a thing that, like in the movies, you discover it's 18 days out, and you're going to do more than say, oh, shit. Where's my wine? Yes, now.
Yeah, I was wondering if you remember how far out and how was the impact? The Comet Temple?
This Comet Temple, I believe, yeah. And I don't remember. I know several of the people who were on the mission, but I don't know what the time between launch. Oh, I think it was years, actually. This is Robbie saying, Morbius, something's coming from the southeast. Yes.
If we do find an object, something that could actually cause the
I'm sorry.
if there's an object we know that's going to hit us and we find out too late, are they even going to bother telling us?
Yes, they will. And in fact, the plans are, if certainly for smaller ones, if say a 50-meter one we're seeing coming in, I mean, chances are it will land, as one fellow said, someplace worthless like Kansas. Now, I pointed out to him that Kansas has 2 senators who may disagree with that. Nevertheless, certainly if the time is short, what they will do is once they have a confirmed region where they think it's going to hit, they will begin looking at how you evacuate people from the target area. And again, for 50-meter ones, that's a small enough area that it may be cheaper, in fact, just to do civil defense.
Could you repeat the questions for people in the
Okay.
audience can hear?
Sorry, the question was, would we be notified if something were seen coming our way and the time was short? And again, I've been in exercises where people have looked at that, and they've had FEMA there, and the instincts are, yes, we start telling people as soon as we have reasonably solid data. That is to say, you know, when they say when the target is large and they say it's somewhere on this side of the Earth, and you know there's not much you can do, they may tell them hold off a day or two and get that smaller before they tell you. But the other reason is in one of the exercises the people were disturbed to learn that the president may learn of the impact threatening from CNN, because the data are entirely unclassified and on the open net. And so amateur astronomers go out and look at what's been discovered lately, and can they see it? Now, unfortunately, my telescope's too small for most of the things they're discovering these days, but occasionally they pick up one that I could go and observe. And again, it will be right on the net in the open for anyone to look. Now, they have, in fact, after that, opened up a channel by which, as soon as the alarm bells go off, which says, yes, something's going to hit, that information goes from JPL to the people at NASA headquarters, who now have a direct line to the White House in the case that something were seen coming.
Yeah, I just wondered if they would, if they cause mass hysteria.
People would no doubt be concerned. But in talking with someone who worked on emergency situations, said that most people actually respond very sensibly when there is a real threat. You know, they respond and they say, what is it I can really do? They go silly afterwards. Yeah.
What is the probability that an asteroid hit the Earth in relationship to the extinction of the dinosaurs? Is that
there is these layers that you have the dinosaur and the fossils, and then the after the tertiary, and there's a big iridium layer there, and that was the first piece of evidence that something hit, because iridium is very rare in the Earth's surface, and most of it comes from things that fall. And so it was clear that something spread an iridium and carbon layer all around the Earth at about this place. Now, the paleontologists originally said, wait a minute, when we said the dinosaurs died out suddenly, we meant any 100,000 years now, not now, but any 100,000 years. Subsequently, looking at smaller fossils that are more common showed big changes in a much smaller time scale. Now, it still doesn't say, well, it was, Thursday that all the fossils stopped. But, it suddenly was a much smaller. Finding the big hole in the ground, while that much iridium suggested there had to be one somewhere, eventually they found it. And the timing is about right. You can argue about the dating on there a little bit, a million years one way or the other, but it looks that it was at the very least a contributor and very bad for the dinosaurs on the American continents. Yeah?
Question from Open Sim Grid. Silver Callow asked, when was the last 1,000 megaton one to hit us?
I can't answer that. As I said, there's only 150 known craters on the Earth. Most of the bodies, even things of tens of thousands of years ago, are in places that we can't find the craters. And so I can't say. We claim that things of that order hit in tens of thousands of years on a statistical argument. When we look out at the things hitting the Earth, we actually see things hitting yearly at the kiloton level. But above that, when you're talking about 100-meter objects, 50-meter objects, 100-meter objects, 300-meter objects, those are hundreds of years apart at the very least. And the ones that would be 1,000 megatons are tens of thousands of years apart statistically. And it's basically done by looking out there, seeing how many there are, and then just running a big Monte Carlo thing of throwing that, that dice that many times and saying, how many times does it whack us? And so, it is an estimate based on the number of them that we see. Yes?
Why do people not want to use nuclear power to do this? What's the negative effects of using nuclear power?
A National Academy panel basically said, if you have a large asteroid, and we would argue about what large means. I would say large was above 300 meters. If you could, on the other hand, launch, if you would build the Ares 5s and could launch 50-ton loads to deep space and could launch many dozens of them in a short period of time, you might push that up to 400 meters. But above that, you have a simple choice. We could try using a nuclear explosive to deflect it, or you can take the hit. And there were many people who are reluctant to discuss it because they see it as legitimizing nuclear in a time where people would just as soon we eliminated them. And I'm not arguing that we shouldn't eliminate them. I would argue it's a good use for nuclear. I'm not saying that we couldn't eliminate them and still either have a UN-held storage of some. I don't care what. I'm just saying right now, the technology we have at the large size, or if you discover it late, if you discover it with only 10 years to go, you have the choices. You take the hit, or you use the nuclear. And the nuclear can do the job. There has been a great reluctance to just consider it even.
Does it stay in space? Can it come back to us? Is there any dangers of putting all that nuclear?
Well, if you talk about sending a nuclear explosive out there, it's the same type of thing that we used to set off here at home. And let me tell you, you set it off out in deep space, that goes away. There's nothing that comes back. Yes?
Dr. Strangelove. Sorry.
Indeed.
Three little questions. One, directly following on from that. I've been on two launches where things have gone up and rather rapidly come back down again when they weren't supposed to. Are you assembling this in space and assembling it on the ground? And what sort of nukes do you send up? Is it, if it comes back down, is it a fairly benign lump of uranium that just sits there, or would it go
modern American warheads, which are not necessarily the same as all other countries. If you send one up and the missile malfunctions and comes right back down, well, first of all, if it were a rocket launch, not because we aren't launching missiles into deep space, you're launching rockets that go further, it would have destruct on it, and yeah, it would not hurt the nuke. The nuke would fall in the ocean, and it would not go off. Okay. In terms of being a benign lump, well, it'd be a lump, and we'd probably go get it.
Would it be a normal nuke, or is it a very special nuke you're having to design for it? And how easy is it to design one of those?
I would prefer, first off, we would not use anything that hadn't been tested robustly. If there's a lot of time, you might choose something that was tested once upon a time but is no longer in the stockpile. You know, even if you had to put it together, because we know what we did once upon a time. And I would prefer the ones that were like in the nearly pure fusion tests, because if you're worried about the radioactivity, which I'm not in this case, you have very little residual radioactivity if you have a nearly pure fusion device. And the pure fusion device puts out more neutrons, and I like neutrons for nudging better than I like X-rays. I can do it with either, but I tell you, if we have 30 years, and just say, well, why don't we make one of those things up that we did the big hole with?
Mike, I have two Newtonian questions now. One is, this is going back to orbital mechanics. You're observing a partial, I don't understand, you're observing a partial orbit and then calculating return. Is that assuming that there's no interaction in the asteroid belt significant from other objects?
No.
The second question is, moth getting off the chest. The second one is, how does that moth get here? No, how accurately can you predict the actual landing of one of these things?
For the first question, when you predict that small arc will be calculated with a standard solar system model that is used that does not include some of the asteroids. Okay, that is a small perturbation that matters in hundreds of years, but not in 10s and 20s and 50-year periods. And so, yeah, they will be including for when they expect a return. They will be including, does that have a close passage with Mars or Venus? In it.
What about with the other, because I was thinking the asteroid field is now looking so packed.
Yeah, well, it depends on the orbit, but they will probably not include the asteroids. But this thing is going around out there and mostly not hitting anything, because even though there's an awful lot, there's 500,000 more members of our solar system than we used to know about. It's still mostly vacuum out there. Yeah, you've had your hand up more.
How strong is a nuke that we can send out there to deflect something? We don't need a demonstration.
Come on.
How old is the Barringer crater?
About 50,000 years old.
That's within almost human perspective, isn't it? Can be. It seems that might have been a worldwide phenomenon. I don't know what Cro-Magnon would say about it. They might have said something. We figure it out. On the caves somewhere.
Not there.
Well, no, I mean somewhere else. Somewhere outside of the Southwest. I don't think there were humans in
Here.
the Southwest 50,000 years ago, but they certainly were humans in Europe.
There's a modern nuke.
Who's standing by that RV?
The guy who was responsible for the cleanup of Bikini Atoll. So that's the size.
How strong is it?
I'm not allowed to say that, but go look in the Wikipedia. I can't vouch that they're good. Let me just say that'll do the job.
And how much does it weigh? Roughly, in unclassified things. More or less than you?
Not a lot more than me. Yes?
So what's the delivery system? I mean, what rockets?
Let's assume that we want to deliver a ton, because you're not going to deliver that. That's meant for throwing and hitting the Earth. And you take the thing out of that, and you probably put it in a vehicle that's akin to the Deep Impact Mission vehicle, because it's got to steer its way. You get it and put it on a big rocket, and you throw it out there, and then it's got to steer its way. You know, it's flung, so it's going to go pretty near the asteroid, but as it's approaching, it has to say, okay, a little to the left, a little high. Okay, so you need something that has sensors on board, that provides a cocoon that keeps this thing that meant to fly in space, but keeps it nice and warm for the trip. And it takes it there, and then as it's approaching, it says, and we're about 2 kilometers off now, 1 kilometer off now, and time to go eventually. And so if you had a mission where you say, oh my God, it's coming, that's actually the slowest piece to have. You can stack a Delta IV Heavy or an Atlas V in 6 months. Even if, you know, I mean, if something like that were coming, the orders would come down that if one's partially built, it's going to be the next one. But that is a many-month thing. Having, you know, ripping the guts out of that one and putting it in a little foam and saying, okay, put this inside your thing and here's the wires. That's pretty fast. The part that's slow is building that thing with sensors that does kind of what Deep Impact Mission did, which was try to say, okay, I'm going to hit it, and you probably want to build it a little better than the Deep Impact, but you know how to do that if money is less of an issue. We understand how to do an active infrared sensing and a radar or a LiDAR diffusing distance so that we can say where it is to centimeters. And so that's the slow part, though. However, it's the same thing you'd need if you wanted to do an impactor. The only thing is the impactor would be a lot heavier than this. Yes?
So if that was to go up on a rocket, would they send up more than one rocket at a time, or would they see if the first one was able to do the job and then send up another one if it didn't?
Especially if you're going, you know, if it's what we hope the situation would be, that is you have decades of warning, you're likely to have you know, several decades of warning, you're likely to have multiple launch windows in that period of time. Maybe fewer than you think. You know, 30 years out, you may only have 3 launch windows, 4 launch windows. And in a launch window, you may launch more than one and target them to arrive at different places along the path. So the first one that gets there is a thing that does some investigation. And it does some investigation, then pulls off, lets the asteroid come along. It meets the first either impactor or nuclear explosive. It then comes back and sees what's happened and checks the orbit, and then it's coming along and it reaches where the second one would have been sent. But you don't want to waste launch windows, so you know you probably wouldn't say, okay, it's 30 years out, let's launch one now. Okay, that wasn't enough. Well, 10 years from now, we'll try another one. So, no, you'd probably not do it that way. Yes?
So the asteroid that came by last Tuesday,
Yes?
I guess it was about 400 meters?
That was the, yeah, I mean, they now probably know very well what it is because it came close enough that you have a real diameter measurement. Before, most asteroids, all you have is a brightness measurement. You know, you see it, it's way far out there, and you see how bright it is, and you know how far away it is, and you say, well, if its reflectivity is some average number, it's about this size. And so most asteroids, that's all we have. In this case, at least after this passage, we certainly know what the diameter is. I haven't seen what it was, but 400 was the number I saw. That's pretty close. Although, if you look back, I've seen several pass between us and the moon in the last 10 years. So, you know, they are happening. There's if you go on the Minor Planets website, they have a thing that actually tracks the Earth around, and it shows all the asteroids, the near-Earth objects that come by it over the course of a year. So you see the Earth's orbit, and you see a little tiny Earth, and it goes around, and then all these things are going by. It looks like you're in a shooting gallery. Now, fortunately, you know, the Earth is small in that image, and the asteroids are small too, most of them. But there's a lot of things going by, and they do hit. It's just rare. It's not a thing that I'm warning anyone, oh my God, we've got to drop everything and work on this. You know, it's something that, because we can do something about it, it's worth thinking about, and it's worth looking at what the options are. And that's really all.
In terms of exercising our options, do you know of any engineering activity or production activity in which we're actually getting a design that we could put this arrow in our quiver?
Again, the nuclear, we are not building anything that, you know, we are refurbishing some things in the stockpile.
I meant the launch vehicles.
The launch vehicles, you know, there are new designs that NASA is pushing for. I don't know. They certainly put out a trial balloon saying, boy, we'd really like this big rocket recently. Whether they ever get money for it, it's going to be another question. It's kind of a hard funding time for that.
So the answer is no, really,
Not at the moment. The Ares series that were talked about were canceled earlier, and so they're now looking at a different series.
Now, the second question is that you mentioned a difference between the prompt X-rays and the neutron. Was that because of the timing of absorption and energy absorption?
It is that the X-rays that are put out, you know, just regular X-rays, if you put them into silicates, they're absorbed in a very, very thin layer. And what happens is you start burning in, but, you know, you may actually only vaporize that much rock. If you put in neutrons, one mean free path may be about that much, and another mean free path is about that much, and so you may vaporize that much material. Now, that much material is not vaporized to as high a temperature, but you get more momentum by heating that much material to a lower temperature, and so I like neutrons better as the source of heating.
So in tuning the device.
You know, the U.S. was known to build things that were optimized for neutron output, and that's about the limits of what I can say on it, other than to say, and fusion produces a lot of neutrons. Yes.
Just about a week or so ago on the Science Channel, they were talking about pop-ups in 2012, and I'm close with April 13, 2029, they said, I think they gave a distance of something like 7,200 miles. Is that correct?
It's, is it that far out? It's inside of geosync.